This is the second half of our chapter on the water solubility of organic molecules. In this lecture, we will review how the water solubility of organic species depends on ionization, temperature, pressure, ionic strength, and the presence of a co-solvent. We begin with a review of the ionization of organic acids and bases. Commonly encountered organic acids include phenols and carboxylic acids. Here, a generic organic acid is represented by HA. In water, it dissociates to produce a conjugate base. The extent of this process can be described with an equilibrium constant more commonly known as the acidity constant, Ka. Here the brackets indicate equilibrium concentrations. The higher the acidity constant, the greater the acid dissociates and the stronger it is said to be. Acidity constants are quite small and are usually reported as power values or p-values. That is, a pKa value is reported for the organic acid, which is the negative of the base 10 logarithm of the acidity constant. Stronger acids have lower pKa values, and generally acids with pKa values of 3 or less are said to be strong acids. The most common organic bases are species possessing amine groups. The same approach can be followed to define a pKb value for these species. However, a more common approach is to quantify the strength of the organic base, denoted here with a capital B, by the strength of its conjugate acid. Stronger bases are those that produce weaker conjugate acids, and strong bases are commonly identified as those producing conjugate acids with pKa values of 12 or greater. Here, pKa values measured at 25 degrees Celsius are listed for a variety of organic acids and bases. Often, approximate pKa values are associated with acidic or basic groups, such as a pKa value of 5 for carboxylic acids. But it should be emphasized that pKa values are strongly influenced by the surrounding chemical structure. Structures that delocalize negative charge to stabilize formed conjugate bases promote the ionization of organic acids and reduce their pKa values. Structures that better accommodate positive charge stabilize conjugate acids, promoting the acceptance of protons, and raise the pKa values of organic bases. When it comes to interacting with water, the conjugate base form of an organic acid behaves very differently compared with its free acid form. For example, the water solubility of the ionized acid is typically several orders of magnitude greater than that of its neutral form. In general, the ionized acid is considerably more stable in water, which greatly reduces its tendency to distribute into adjacent phases or adsorb onto contacting surfaces. The ion behaves like a completely different species than the acid, and for good reason, it is. In fact, when an organic acid or base is at a pH where it is distributed between its neutral and ionized forms, it is said to have undergone speciation, and the behavior of both the neutral and ionized form must be taken into account in determining the added molecule's overall behavior or impact. The fraction of the organic acid present in its free acid form, denoted alpha A, is calculated from the acid's pKa value and the solution pH using the Henderson-Hasselbalch equation. 1 minus alpha A is a fraction of the organic acid present in solution in its conjugate base form, which is its ionized form. Here, the degree of ionization for a weak organic acid with a pKa of 7 is plotted as a function of solution pH. Points composing the curve were calculated using the Henderson-Hasselbalch expression. A good approximate curve can be constructed using a few observations from the equation. First, note that the curve has a sigmoidal shape. In this case, the amount of acid ionized increases with pH, so it's an increasing sigmoidal curve. Second, when the solution pH is equal to the pKa of the organic acid, it's 50% ionized. Finally, the equation indicates that when pH is 2 units below the pKa value, more than 99% of the acid molecules are in their acid form. And when pH is 2 units above the pKa value, more than 99% of the acid molecules are in their ionized form. These results allow for a rapid and accurate sketch of the degree of ionization with only the pKa value for the organic acid. For organic bases, 1 minus alpha A is a fraction of chemical in its neutral base form. When the base picks up a proton, forming the conjugate acid, it takes on a positive charge. so the degree of ionization of an organic base is calculated from the expression for alpha A. Note the difference compared with organic acids where 1 minus alpha A is used. Here the ionization for an organic base, alpha A, with a pKa value of 7 is plotted against solution pH. Again, points composing the curve are calculated using the Henderson-Hasselbalch expression. The same guidelines for sketching the ionization curve for an organic acid applies for the base with a few modifications, given that for an organic base, the degree of ionization is a decreasing sigmoidal function. That is, for the organic acid, ionization increases with pH, while for an organic base, ionization decreases with pH. The ionization of organic acids and bases greatly enhances their water dissolution. For organic acids, we distinguish the water solubility of the neutral form, the free acid, from its conjugate base with the additional subscript HA. If the pH of the aqueous solution is within 2 units of the organic acid's pKa value, the acid will undergo some degree of dissociation. The water solubility of the formed conjugate base, designated here with the subscript A-, is substantially greater than that from its free acid form. We will assume that the ionized form is completely miscible in water and will reside exclusively in the aqueous solution. With this assumption, we can write an expression for the total water solubility of an organic acid, which takes into account both the acid and conjugate base, indicated with the added subscript total. This is obtained by simply dividing the water solubility of the free acid form by the fraction of the organic acid in its free acid form at the solution pH. A similar approach is used to develop an expression for the total water solubility of an organic base, which takes into account both the base and conjugate acid. In this case, the water solubility of the neutral base is divided by the fraction of the organic base in its base form at the solution pH. The example demonstrates a straightforward calculation of the total solubility of an organic acid when it is partially ionized. We are asked to calculate the maximum concentration of solid phenol that could dissolve in water at 25 degrees C for a pH of 9, given its solubility and pKa values. It is important to note that unless explicitly indicated, provided solubility values are assumed to be for the free acid form of an organic acid and the base form of an organic base. This is the case for most reported properties when organic acids and bases are involved. For this calculation, we simply divide the provided solubility by a fraction of the phenol in its free acid form at pH 9. It is instructive to plot the total water solubility of phenol as a function of pH. Up to 2 pH units below its pKa, the total solubility is equal to that of the free acid, because none of the conjugate base is present. After this, the phenol begins to ionize, and the formed ionic species readily dissolves into the aqueous phase, sharply increasing its total concentration in the aqueous solution. We could have also found the value we needed at pH 9 from the curve. To assess water solubility's temperature dependency, we apply the Van Hoff equation, which relates the equilibrium constant for a chemical reaction to absolute temperature through the associated enthalpy change. We apply the equation's integrated form under the assumption that the enthalpy change is relatively constant over the temperature range of interest. This assumption requires that the temperature range be reasonably small and not include a phase transition. The reaction or process of interest to us is the distribution of an organic molecule between its pure liquid phase and an aqueous solution. We estimate the equilibrium constant from its water solubility. The enthalpy change is the excess enthalpy of dissolution. This expression's integration provides a model equation for the temperature dependency of water solubility involving liquid organic solutes. According to the equation, the logarithmic plot of a solute's water solubility versus the inverse of absolute temperature should produce a straight line from which we can extract the excess enthalpy of dissolution. For organic liquids, water solubility can either increase or decrease with temperature. In cases where the excess enthalpy is positive, the solubility increases with temperature. When the excess enthalpy value is negative, solubility decreases with temperature. However, in general, it is observed that the temperature dependency of water solubility values for the dissolving organic liquids tends to be weak. This example demonstrates the fitting of solubility versus temperature data for a neutral organic liquid. It asks us to use the aqueous solubility temperature data listed for chloroform to estimate the excess enthalpy of dissolution and aqueous activity coefficient at saturation at 5 degrees C. The data is over a range of 0 to 30 degrees C for which chloroform is a liquid and does not undergo a phase transition. The solubility values are provided in terms of mole fraction, which could be used. But let's convert to molar values by dividing by the molar volume of water. Also, we can list the natural log of solubility values and invert temperatures after converting to degrees Kelvin. A plot of the natural log of the solubility versus 1 over T produces a straight line for which the equation is provided. The positive slope indicates that the water solubility decreases with increasing temperature in this region, and that the excess enthalpy value is negative. Given that chloroform has the ability to form hydrogen bonds with water, this result should not be surprising. From the equation for the line, we estimate the solubility of chloroform at 5 degrees C, and with this, the activity coefficient at saturation. The dependency of water solubility on temperature for organic solids and gases tends to be more significant. When considering neutral organic species that are solids in the temperature range of interest, the enthalpy change must take into account the phase transition to form a liquid. The heat of melting is endothermic and usually large relative to the excess enthalpy of dissolution. So plots of the logarithm of water solubility versus inverse temperature tend to possess negative slopes, and the water solubility of organic solids tends to increase with increasing temperature. This is a result that is likely familiar to you. When considering neutral organic species that are gases in the temperature range of interest, the enthalpy change must take account for its condensation to form a liquid. The heat of condensation, which is the negative of the heat of vaporization, is exothermic and typically large relative to the excess enthalpy of dissolution. So plots of the logarithm of water solubility versus inverse temperature tend to possess positive slopes, and the water solubility of organic gases decreases with increasing temperature, again a result that is likely familiar to you. The figure, which is from a New Zealand fishing site discussing the effect of oxygen levels on the behavior of different fish species, plots the solubility of oxygen in both fresh and salt waters as a function of temperature. We are asked to extract and plot data for both the fresh and saltwater systems to show that the equation developed for organic gases can be used to model the observed behavior. Interpolation is used to obtain solubilities at 10, 20, 30, 40, and 50 degrees C. These values and the corresponding temperatures are converted into the desired form in units. As expected, the slopes for both lines are positive, consistent with the exothermic condensation of the oxygen and a decrease in solubility with increasing temperature. The lines are parallel, and the shift, that is, the difference in their intercepts, are due to the decrease in oxygen solubility with increasing electrolyte concentrations, which will be discussed shortly. Often omitted from discussions on the water solubility of organic solutes is the influence of pressure. For organic liquids and solids, this dependency is not strong, and the exclusion is often justified. However, understanding the reason for the weak dependency is instructive. Furthermore, there are situations in colloid science where differences in pressure promote the destabilization of nanoscale particles, and decreases in solubility due to pressure changes can create serious issues for industrial processes such as pressurized reactions. The equation shown relates the equilibrium constant for a chemical reaction to absolute temperature through the reaction volume, delta V. For the dissolution process, delta V is the partial molar volume of the liquid solute in water minus that in its nearly pure organic phase, which we will take to be the pure molar volume. A search of published partial molar volumes for organic solutes in water at infinite dilution indicate that this value is typically slightly lower than their molar volumes. From the integrated forms of the equation, this indicates that water solubility increases slightly with pressure. For organic solids, the same equation applies, but it is helpful to divide the molar volume of the solid into that for the molar volume of the supercooled liquid and the change in molar volume associated with the melting transition. This value will be positive, and usually greater than the difference between the partial molar volume for the solute in water and the molar volume of its supercooled liquid. From the integrated equation, this indicates that the water solubility of organic solids tends to decrease with increasing pressure. Again, for both organic liquids and solids, the dependency of water solubility on pressure is not strong, but it can become an issue under certain circumstances. For organic gases, the dependency of water solubility on pressure is more significant and important to a wide variety of products such as pressurized beverages and foams. The same equation applies. We divide the molar volume of the gas to explicitly list the volume change associated with the condensation process, here given as a negative of the change associated with vaporization. The molar volume of the vapor is substantially greater than that of the liquid, which can be neglected, allowing us to apply the ideal gas law. Converting the ratio of total gas pressures to the ratio of partial pressures and integrating results in a linear relationship between the water solubility of the organic gas and its partial pressure through a constant. This is known as Henry's law constant, which is dependent on temperature. Thus, unlike organic liquids and solids, the water solubilities of organic gases are strongly dependent on pressure. The example is asking us to determine the difference in the water solubility of carbon dioxide for a fixed temperature of 3.9 degrees Celsius at 2 atmospheres versus 25 degrees Celsius at atmospheric pressure, which we will assume is 1 atmosphere. We have the Henry's law constant at 25 degrees C, but not at about 4 C. We can look this value up, or it can be calculated. A quick search provides an equation for estimating the Henry's law constant for CO2 and water at other temperatures using the provided value. With this value, we can calculate the solubility of CO2 and soda at both 2 atmospheres and 1 atmosphere. The difference between the calculated solubilities multiplied by the volume of the can provides an estimate of the released carbon dioxide. We next examine how water solubility is impacted by the presence of ionic species such as sodium, magnesium, calcium, sulfate, etc. Ions generally decrease the aqueous solubility for sparingly to moderately soluble organic compounds. This effect, known as salting out, is found to depend both on the specific organic solute and the salt. Shown here is an empirical relationship established by Sechenau, which relates solubilities of organic compounds in aqueous solutions containing ionic species to that in pure water through the Sechenau constant and the molar salt concentration. For mixtures of salts, it is found that the effect is additive, and Sechenau constants can be determined via an additive expression in terms of mole fractions. The salting out effect can be explained, at least qualitatively, as resulting from the strong hybrid interactions between ions and water, discussed in the previous chapter. As a result, added ions consume free water in aqueous solutions to construct hydration shells. This consumes the free water molecules that would otherwise participate in the formation of clathrate-like hydration shells to solvate less soluble components of organic solutes. The fact that ions that form larger hydration shells and more nonpolar solutes provide for the greatest salting out effect is consistent with this mechanism. The influence of ions is significant. A familiar example is the ability of salt water to reduce the solubility of an organic solute up to 50% relative to its solubility in pure water. It should be noted that a salting in effect is also possible, but is more likely a result of direct interactions between solute and ion. The effect tends to occur for highly polar organic species and larger organic ions. One last comment is that the salting out effect is relatively small for salt concentrations found in natural and tap water, but climbs exponentially and can be significant for high salt levels. For example, industrial waters such as those that are used in the processing of pulp and paper have very high ionic strengths. The example outlines the estimate of caffeine solubility in water containing 0.6 molar of a salt, given its solubility in clean water at 25 degrees Celsius. The salt is a combination of 3 salts, all present at equal mole content in the solution. Using the constants for the individual salts and their mole fraction, a composite Sechenau constant is determined. The solubility of the solute in the salt solution can then be estimated from the Sechenau equation. When a second organic species is added to water, Its impact on the solubility of an organic solute is relatively minor until its concentration is greater than about 5 to 10 volume percent. Its ability to dissolve at such high levels means that it is much more soluble than the organic solutes of concern to us. In fact, we will categorize organics added to solution at levels above about 5 volume percent as co-solvents. The presence of a co-solvent tends to enhance the water solubility of organic solutes. The empirical equation shown relates the logarithm of the ratio between the solubility of an organic solute in water containing a co-solvent and that in pure water to the concentration of the co-solvent in terms of volume percent. The proportionality constant, sometimes called the solubilizing power factor, is dependent on both the solute and co-solvent, and its values are less than 1 in units of inverse volume percent. In general, more polar co-solvents provide larger constants for a given organic solute. The co-solvent is believed to work by breaking down water structure, essentially turning water into a typical run-of-the-mill organic solvent rather than a highly structured liquid. In solution, co-solvent molecules likely compose a major portion of the hydration shells of organic solutes and play a significant role in the dissolving process, greatly increasing their solubility. The example provides data for the water solubility of phlosterone as a function of added ethanol concentration. We are asked to plot the data and report the solubilizing power factor. Both linear and nonlinear plots are provided. The log-linear model we reviewed provides a good fit of the data for which the solubilizing power factor is the slope of the resulting line. Before we end, let's review a little and discuss the implications of what we've learned. We spent much of the first lecture discussing the solubility of sparingly to moderately soluble, neutral organic molecules in water. The objective was to provide the quantitative thermodynamic framework for describing their dissolution, which led to a set of qualitative rules for making comparisons and understanding differences in solubility behavior. Our current lecture focused on the dependency of water solubility on ionization, temperature, pressure, salts, and co-solvents, which we summarize in general terms here. The movement of chemicals through nature and often through industrial systems is controlled to a large extent by water solubility, and limited water solubility is what often necessitates colloidal systems. This is one of the main reasons I have included the topic of water solubility in this course. But the variables and interactions we identified as influencing water solubility of organic solutes have a more general impact on aqueous systems, including colloids. As we will discuss shortly, aqueous colloids are composed of insoluble particles dispersed in water. The interactions between organic solutes and with water, which determine their stability, remain relevant when molecules form particles, and these also determine particle stability, in this case, kinetic stability of a colloid. For example, we discussed that changing the pH can lead to the ionization of organic acids and bases, which changes their interaction with water. Ionic species are substantially more stable in aqueous systems. We will find later that charging of particles through the same mechanism or via adsorption of charged species stabilizes particles in aqueous environments. We also reviewed how ions present in water reduce the solubility of organics when their concentration is high enough. For colloidal systems, we more commonly characterize the presence of ions using ionic strength, designated here with Cap-I, which can be calculated for known salt compositions. The presence of ions dissipates electric fields, reducing the stability of charged particles in aqueous colloids, or absorb onto surfaces to enhance or limit charge density, modifying stability. The point is that many of the same core variables and interactions identified here will reappear throughout the course as we move further along in our discussion of colloidal science. These include pressure, temperature, the charge on species and surfaces, the concentration and composition of ions, and the presence of co-solvents that modify water structure. Understanding their influence on molecules will later help us understand their impact on complex colloidal systems. This completes our chapter on the water solubility of organic molecules. If you have any questions, comments, or corrections, please contact me at the address below.